Let us try and understand why this function e doesn't work with n equal to 14. With n equal to 13, it seems to be working fine, and so we're running this for loop 13 times and everything is fine. But then in the 14th iteration, something bad seems to be happening. Now, you might look at the statement inside this for loop, sum plus equals this expression on the right, and you might say, oh, wait a minute, the expression on the right is a mixed expression because power returns a double, factorial returns an int, and maybe there is something messed up over there. Well, the int factorial is going to be implicitly typecast as a double, and we're going to do division by doubles. So that should not be a problem. But let's try and look at these values of n a little bit more carefully. So when n is 13, the last value inside this for loop, the largest value of I inside this for loop is I equal to 12, right? And when we look at the case with n equal to 13, this calculation seems to be producing a good answer. So it's calculating x to the power 12 divided by 12 factorial. Let's just quickly pull up our calculator here and figure out what 12 factorial is. It's going to be a big number. There you go. It's about 479 million, right? So that's a big number, but it's still within the limits of the int, which is, remember, up to about 2 billion. But in the next iteration, when n is 14, so then I will go up to 13, and then we'll calculate 13 factorial. Now 13 factorial is this number times 13. And if this is already half a billion almost, then 13 factorial is going to exceed our 2 billion limit. So this seems to be the problem. So 13 factorial is 6.2 billion. Now we know that when you exceed the upper limit, you are going to wrap around to the negatives. So if this 13 factorial is going to be a negative number, then when we try and add a term with a negative denominator, we should get a negative term. So in fact, the sum should become even smaller, but it's not. It's becoming bigger, and it's becoming even bigger than the actual answer. So what's going on? Well, we have to think very carefully about this number 6.2 billion. Yes, it's so big that we can't represent it as an int. So we know that when you exceed the upper limit of the int, you wrap around to the negatives. But then you continue from there, and 6.2 billion is so much larger than the upper limit that not only do you wrap around and go negative, but then you proceed from there for another 4 billion steps, and so you end up back in positive integers. Now, we cannot represent this properly. The true value we wanted to represent was 6.2 billion in the denominator. And what we're actually representing is a smaller positive integer in the denominator. So if we have a smaller number in the denominator, that means the term is actually bigger, and that is why we are exceeding the limit. So it was not an easy explanation to try and understand, to figure out exactly where the bug was. But this is why we have to be so careful with exceeding the limits of the calculation. And this was really what I wanted to highlight here, that not only is this code slow, but it also has this very subtle error. Anyway, we know we want to fix this code because this is calculating in a very wasteful way. We have discussed that the I plus first term in this calculation is just a simple variant of the ith term. We just have to take the ith term, multiply it by x in the numerator, and divide by I plus 1 in the denominator. We shouldn't keep calling these power and factorial functions again and again. That is slow. So let's just make that fix, and hopefully that will also fix the other problem that we have. So here we are in the IDE, and we don't want to do all this. So let me get rid of it. Instead, we want to remember the current term, right? And we just want to remember the current term and add it to the sum. So let me make a variable called term, right? And what is the first term in this series? What should I initialize this variable to? Well, the first term in the series is x to the power 0 by 0 factorial. Right now, I'm assuming that x is non-zero. So x to the power 0 is 1. 0 factorial is, by definition, 1. So this is 1 by 1. So it's 1. So I'm going to initialize term to 1.0. That's my initial value of term. And what I'm going to do in the for loop is I'm just going to add this term to the current total sum, and then I'm going to update term. So I'm going to say the new value of term is, I'm going to use this idea that in the next iteration, the new value of the term is the current term times x divided by I plus 1. So is the current term times x divided by I plus 1. And I save that, and this should be my code. I mean, if you want, I can even, instead of saying term is equal to term times, you can use the times equal to, if you wish. This seems a little bit easier to read even. So that's what we're going to use. So let's save this version and let's compile it. So let me exit this old code and compile it. My file is called exp.c, and I can run it. So now I'm running the new code. So when I run it with n equal to 13, I get quite close. I got this close even with the old piece of code. Now I'm going to try it with n equal to 14. And now it works. I mean, we have got even closer to the true answer. We have more zeros. If I go n equal to 15, I get even closer. 16, even closer. 17, well, I'm almost there. Okay, so let's see what happens with n equal to 18. Maybe we hit an error of 0. Oh no, again we have a negative error. Now this is going to take us way beyond this basics of programming. We would really have to understand these calculations about double and floating point values more carefully to understand why we're seeing this small error. I'm sorry, I cannot get into the discussion of this in this basic introductory course. So let's just accept that we got pretty close to the true answer. So our point anyway was to understand loops better, and we were using this as an example to understand and improve our proficiency with writing code with loops. And we will continue to write code with loops because this is very important, and much more practice is necessary. You have seen that the way in which you initialize variables matters a lot. The way in which we write our loop conditions matters a lot. So we need much more practice, and that's what I'm going to give you in the next few lectures.